This video is a review of electric charge, force, and circuits for AP Physics 1. To start, I'd like to talk a little bit about where electric charge comes from and how it gets factored into physics problems. So we know that all matter is made up of protons, neutrons, and electrons. And while neutrons are electrically neutral, and therefore, they can't contribute any charge, and they don't exert electric forces on other charged particles, protons and electrons do have a charge, and that charge is equal in magnitude on the proton and the electron, but opposite in sign. And the magnitude of that charge is 1.6 times 10 to the minus 19 coulombs. And so maybe that helps us remember that charge is measured in coulombs, which is represented by a capital letter C. So the charge on the proton is positive 1.6 times 10 to the minus 19, and the charge on the electron is minus 1.6 times 10 to the minus 19. And although the electron is a small thing, and the proton is a small thing, we see that the amount of charge on an electron or proton is quite small. And that's partially due to the fact that a single proton or electron doesn't have very much charge, but it's also due to the fact that a coulomb is an incredibly large amount of charge. And so for that reason, sometimes we end up working with units of nanocoulombs or microcoulombs. Nanocoulombs is times 10 to the minus 9 coulombs, and microcoulombs is 10 to the minus 6 coulombs. And so sometimes units of charge will be given in those units instead of just coulombs. Most ordinary objects don't have a charge. We say that the net charge on those objects is 0. And for that reason, we call them a neutral object. They have the same amount of positive charge as negative charge. So it's not that there's no charge present in the object, it's that the amount of positive and negative are canceling each other out, making the object neutral. And so how do I charge an object is a question that we need to be familiar with. So if an object becomes charged, then it either has an excess of electrons or it has a deficiency of electrons. Electrons have been removed. And so the way that I can add electrons to an object or remove electrons from an object is, in one way, charging by friction. If I charge an object by friction, what that means is I'm taking two objects and I'm rubbing them together. And due to the contact between the two surfaces of those objects, electrons will get transferred one way or the other. And there's no reason why you should know which way the electrons are going. So for example, if I take a balloon and I rub my head with the balloon, electrons are either getting transferred from my hair to the balloon or from the balloon to my hair, but I don't know which way the electrons are going. All I know is the amount of electrons gained by one of the objects is lost by the other objects because charge is conserved. And if charge is conserved, then the amount of positive charge on one object is always going to be equal to the amount of negative charge on the other object, assuming that they've been in contact. And importantly, because of the structure of the atom, right, that is, all of the positive charge and neutrons are in the center of the atom, and the negatively charged electrons are around the nucleus of the atom, it's the electrons that are exchanged between objects when they come into contact. Protons are held tightly in the nucleus, they can't be removed, but electrons can be exchanged between two objects. And since an electron is a finite particle that has some amount of charge, as it's exchanged between two objects, it is impossible for an object to have a charge that is not a multiple of an electron. So what I mean by that is I can take one electron and take it off of an object and give it to another. And now the magnitude of the charge on both of those objects is 1 times the charge of the electron. If I take another electron away from that object and give it to the other, now they have a charge of 2 times the magnitude of the charge of the electron. And so in this equation that I've written, n represents the some integer number, and E represents the charge on the electron or the proton. And so the charge on any object is some multiple of E. And I can't have an object have a charge of some fraction of E because I can't split up the electron. In principle, there are two types of objects. Objects that allow the flow of charge to happen very easily, and objects that tend to prevent the flow of charge. And the objects that allow the flow of charge we call conductors, and the objects that prevent the flow of charge we call insulators. And so some objects do a good job of not transferring charge or holding on to their charge, and some objects do a good job of allowing charge to be transferred or moved around within an object. And maybe you remember that in principle, what we say is that metals are good conductors, because if I have a metal, then there's lots of positive charge, but there's lots of negative charge. And in fact, many of those electrons are loosely attached to the atom, and for that reason, if I have a long copper wire, for example, all of those copper atoms have electrons that are very loosely attached. In fact, we call it a sea of electrons, or we call them mobile electrons that are not really attached to any of the atoms, and so they're free to move around. But an insulator doesn't have those same properties. All the electrons are more well attached to the atoms of the insulating material, and so they don't move around as much. If I get to the point where there are a couple of objects that have a charge, then those two charged particles exert electric forces on one another. So anytime there are two charged particles, they can exert electric forces on one another. And it only works if there are two. In the same way that in order for there to be a gravitational attraction between two objects, they both have to have the same, not the same mass, but they both have to have mass. In order for there to be an electric force present, there must be two things that have a charge. And the equation that we use to represent electric force is called Coulomb's law, C-O-U-L-O-M-B-S, law, Coulomb's law. And Coulomb's law says that any pair of two charges will exert a mutual electric force on one another if the centers of those two charges are separated by a distance r, and the charges are Q1 and Q2, then the electric force is given by Coulomb's law, which is the equation in the red circle. And we notice that Coulomb's law is proportional to 1 over r squared. We call this an inverse square law. And another inverse square law that we know is the equation for the gravitational force, which is also proportional to 1 over r squared. For gravitational force, it depended on the universal gravitational constant g and the product of the masses. Coulomb's law depends on the product of the charges and Coulomb's constant. So these are both inverse square laws, which means that if we plot the force as a function of separation between the two charges, then we'll get a graph like the one that I have shown there. If the two charges have opposite sign, then the force between them will be attractive, because opposite charges attract. And if the charges have equal sign or the same sign, then the force will be repulsive, regardless of whether they're both positive or both negative. But regardless, that electric force will always be exerted along the line connecting the two charges. And those electric forces will always be the same, regardless of whether Q1 is greater than Q2 or Q2 is greater than Q1. And they will always point in opposite directions, either toward one another or away from one another. One of the assumptions in Coulomb's law is that Q1 and Q2 are point charges. And what that means is the size of the charge needs to be much bigger than the separation distance between the two charges. So for a proton and electron, that works out very well. if I have a proton and an electron separated by some measurable distance, then the size of those charges compared to the separation distance between them, the size of the charges is going to be much smaller than the separation between them. However, we've done a couple problems where maybe we're dealing not with a proton and an electron, but with two spheres that have a large physical size, and maybe they're moving closer toward one another. And there are some cases where the separation between the centers of those spheres will become small enough that the two surfaces of the spheres will start to polarize one another and redistribute the charge within the object. And for that reason, the electric force changes, and Coulomb's law can't really be applied. So you need to remember that Coulomb's law requires that the two charges be point charges, which means that the separation distance needs to be much bigger than the sizes. And so I suppose in my assumption line written there that I have written that incorrectly. It really should be that in order for the electric force to obey Coulomb's law, this 1 over r squared relationship, the distance between the two objects needs to be much bigger than the size of the objects. So that was written backwards. What I'm crossing off there, the size being greater than the separation between the objects, that would be the case where Coulomb's law does not apply. And one way that we would be able to think about that experimentally is if I made a graph of f versus r squared, which is supposed to be the relationship between f and r for Coulomb's law, then I should get a straight line. But if I notice that there was a deviance either one way or the other, then I know Coulomb's law is not being obeyed. And one way to account for that is, as I said, the two spheres getting close to one another and the polarization of the two spheres coming into play. So we just talked a little bit about how if I take two objects and I rub them together, then electrons can be transferred between those two objects by physical contact. But I can also induce a charge in an object without having to rub them against one another, and we do so because of polarization effects. And this can occur in both conductors and insulators, so I have two examples. First, I'm going to take this balloon on the left-hand side, and I'm going to rub it against something. So I am going to charge the balloon by friction, and maybe in charging it, it acquires a negative charge. So what that means is whatever I rubbed it against acquired a bunch of positive charge because a bunch of the other object's electrons are now attached to the balloon. So I take this balloon and I put it next to a wall, and the wall does not have a charge. Nobody's rubbed it. It has equal amounts of positive and negative charge, and it's more difficult to remove the charge from the electron or from the wall because the wall is an insulating material. But when I stick the balloon to the wall and let go, it stays there. The reason why it stays there is because in the wall there are a bunch of atoms, and those atoms have electrons that are moving around, or can be modeled as moving around like this. And as they're moving around, they are going to be repelled by the electrons in the balloon, the excess of electrons that are in the balloon. And for that reason, the electrons will start to get deformed like this and become more ovalish. The electrons will spend more time on the far side away from the balloon than they will on the side close to the balloon because they are repelled by the balloon. In essence, as the electrons wrap around toward the balloon, they would get sort of slingshot back to the other side and spend more time on that side. And so for that reason, if you imagine many atoms in the wall all doing this, then effectively there would be more negative charge away from the balloon and more positive charge toward the balloon. So not that the positive charge actually moved or moved around or were moved out of the atoms. It's just that by consequence of the electrons spending more time on the right-hand side, there's more positive charge on the left-hand side. Therefore, because of the fact that the positive charge is closer in proximity on average to the negative charge than the other negative charges. There's an attractive force that can exist between the balloon and the wall. And so in summary, a negatively charged balloon sticks to an insulating neutral wall because it polarizes the atoms in the wall. Second, I have an example where I've charged a rod, and maybe I've charged that rod by rubbing it with a piece of something, and that rod becomes positively charged when it's rubbed. And so I hold that rod near an aluminum can that's turned on its side. And what you would find is that the can will start to roll toward the rod. The can will always move toward the rod, and this is true even if I replace the positively charged rod with a negatively charged rod. And here's why. Regardless of whether the rod is positively charged or negatively charged, the electrons in this aluminum can, which is a conductor, are free to roam around. It has mobile electrons that are free to move. And those mobile electrons, if the rod is positive, those mobile electrons will move toward the rod. And if the rod is negatively charged, the mobile electrons will move to the opposite side of the can. And so for the case that I drew initially, the rod is positively charged, and so a bunch of those electrons are attracted to the rod and come to the right-hand side of the can. And by consequence of that, the left-hand side of the can becomes positively charged. Again, not because the positive charge can move around, and not because there are protons that were ejected from the atoms, but for the reason that the electrons left the left-hand side of the can to go to the right-hand side, there is a deficiency of electrons on the left-hand side of the can. Therefore, it becomes positively charged. So in summary, a positively charged rod or a negatively charged rod will attract a neutral conducting aluminum can, causing it to roll. And lastly, I want to point out that even while the balloon is sticking to the wall and while the can is rolling towards that rod, neither one of those objects actually has a net charge. And we need to be careful about the phrase net charge. If I counted all of the electrons and protons in the wall and all of the electrons and protons in the aluminum can, in both cases, the net charge of those objects will be zero. They don't have an excess or positive or negative charge. All that's happening is the negative and positive charge is, it's being polarized or moved around in order to create an attraction between two objects. So this is the essence of induction and polarization. Now I'd like to shift focus to talk more about electric circuits. So we know that batteries have a potential difference across their positive and negative terminals. If you look on a battery, it might say something like 1.5 volts. That is describing the magnitude of that potential difference across those two terminals. And that difference in potential is what provides the electromotive force that drives the electrons through the circuit. And so without an electromotive force, no charges are going to move. And without connecting the two terminals of that battery to allow a route for charge to go from the positive to negative terminals, the charge will not move. So in order to have a circuit, I need to have a closed loop of conducting material, and I need to have a battery that provides an electromotive force. In general, when that happens, current will flow. And because electrons are the things that are moving, current is due to the flow of those electrons. And in general, we say that current, which is represented by the letter I, is the rate of flow of charge, or delta Q over delta T. It's a measure of, in my circuit, how much charge is passing a point in a certain amount of time. Since charge is measured in coulombs and time is measured in seconds, then the unit for current is amps. And finally, I like to say about current that conventional current, the direction that current travels by convention, the way that we define the direction of current, is the direction that is opposite the direction of electron travel. which means that electrons would want to go away from the negative terminal of the battery, so they would go this way. And so, by definition, conventional current comes out of the positive terminal of the battery. Okay, so it goes this way. As charge flows through any material, it collides with other atoms, and because of those collisions, there's some resistance inside of materials. Now, some materials have very low resistance. The things that we make circuits out of that are conducting materials, like copper, have extremely low resistance. But most ordinary materials have some greater amount of resistance. And so in general, for regardless of what kind of material I'm looking at, how could I figure out how much resistance a chunk of something has? There's an equation for resistance that depends on three things: the resistivity of the material, the length of the material, and the cross-sectional area of the material. The resistivity is represented by the Greek letter rho, which is RHO. And the resistivity has units of ohms times meters, and it is a constant for a given material. And what that means is, if I have something made out of copper or aluminum or graphite or whatever, there is a particular resistivity that each one of those materials has, similar to how different materials have different densities that can be used to identify those materials. Resistivity could also be used to identify a material. There is a dependence on the resistivity that can change the resistivity a little bit, that has to do with temperature. And so there's a relationship there between resistivity and temperature, but we will typically think of resistivity as being constant and depending only on the type of material. The total resistance of a circuit element depends also on the length and the cross-sectional area. So as I have shown in the picture below, the length of this material is just its physical length from left to right. That would be measured in meters. And the cross-sectional area means if I were to chop this thing in half and look at the inside of it, what is the shape or the area of that cross-section of material? And so in this case, I've drawn a cylinder, and the cross-sectional area of a cylinder is a circle. And so I could find the cross-sectional area, capital letter A, by using pi r squared as my equation for the area of that piece of material. And we learned that this equation can be linearized like any other equation to provide a straight line where the slope of that line is the resistivity. And the way that I accomplish that is if I could hook this piece of material up to a circuit and measure the resistance, and then for each trial of the experiment measure the length and area of each piece of material, then I can plot this on a graph, and I should produce a straight line, and the slope of that line will be the resistivity of the material. And I know that should be fairly constant because the resistivity is supposed to be constant for a given material. And the way that that works in general is that if I plot if I plot the resistance on the y-axis, and if I plot length divided by area on the x-axis, then the slope will be the resistivity. And hopefully you can see how that matches up with the equation up above. Now that we've talked a little bit about potential difference, voltage, current, and resistance, we can talk about Ohm's law. Ohm's law describes the relationship between the potential difference, current, and resistance of a circuit element in a circuit. And what Ohm's law says in particular is that the voltage across a circuit element is directly proportional to the current through it. And so what that means is, if I created a graph of voltage versus current, if they're directly proportional to one another, I expect that the slope of that graph will be a straight line. And by Ohm's law, we know that that straight line, the slope of that line, would represent the resistance of the material. And that's shown by the Ohm's law equation, right? If I plot voltage on the y-axis, current on the x-axis, then the slope should be the resistance. Therefore, V is proportional to I, the slope of the graph was linear, and so we could call this an ohmic material or an ohmic circuit element. And so if all of those voltage and current measurements were made of a resistor in a circuit, for example, then we could say that this resistor is ohmic because the slope is constant. If I measure the voltage and current across an object and I don't get a straight line, then that means as I increase the current, the voltage did not increase at a linear rate. It deviates from that line as is shown in the graph on the right, and for that reason the graph is nonlinear. And if the graph is nonlinear, that means the resistance is variable, and therefore the object could be said to be non-ohmic. And the point that I have below is that actually most real circuit elements, like light bulbs and resistors, are ohmic at low currents. So ohmic at low currents. But as I tend to turn up the current, these objects are going to heat up. And as they heat up due to those high currents, the resistance is going to change. Right? Maybe you remember thinking about the resistivity equation just a minute ago, and the resistivity of the material can increase or decrease depending on the temperature. And so if I'm having these large currents, then the resistance of the material might be fluctuating with those high currents. Therefore, if the resistance is fluctuating, then it's not constant and Ohm's law is not obeyed. So if light bulbs are getting really hot, or if resistors are getting really hot, then maybe Ohm's law is not obeyed and they become non-ohmic. But sometimes, even for something that's non-ohmic at high currents, it's valuable to take a graph like the one on the right and use the linear region, the region where it does obey Ohm's law at low currents, to figure out what the resistance is in the region where it's ohmic at those low currents. Regardless, if you want to do something like this, you need to perform an experiment. And so I'd like to briefly review, if I have a circuit and I have a resistor in that circuit, how I could make measurements of the voltage across that resistor and the current through that resistor. And so first I want to remind you that in a circuit, the symbol that I use for a voltmeter, which measures voltage, looks like this. It's a circle with a V through it. And then the symbol that I use for an ammeter measures current, is a circle with the letter A in it. And so in my circuit, how could I represent that I'm including those meters in the circuit in order to make some measurements? The way that I could measure the voltage across this resistor is I hook up the voltmeter in parallel with the resistor. And the reason why I'm able to do this is because two things in parallel always have the same voltage. Two things in parallel always have the same voltage. And that is because voltages or differences in voltage are associated with differences in two different points in a circuit. And so even though these are two different things, a voltmeter and a resistor, they're attached to the same 2 points. If I call those 2 points A and B, the voltage between points A and B is the same whether the voltmeter is there or not. Okay. And the reason for that is that voltmeter is designed to have infinite resistance. So the voltmeter is designed to have an infinite resistance. And so let's think about what that might mean and why that matters when I'm making measurements of voltage. If I attach the voltmeter there and it didn't have any resistance, let's say it had 0 resistance, then all of the charge would immediately flow around the resistor through the voltmeter back to the battery. And that would create a short circuit, which can cause the battery to run out of usable energy very quickly. If it had some normal amount of resistance, then there would be essentially 2 resistors in parallel. The equivalent resistance of those 2 resistors would be different, the current in the circuit would be different, and it would manipulate the thing that I'm measuring. The only way that I can add a measuring device that measures the voltage that doesn't affect the circuit is if it has infinite resistance, which means when the charge comes out of the battery and gets to point B, its only choice is to flow through the resistor. It has no choice. It can't flow through the voltmeter. Therefore, the presence of the voltmeter does not influence the voltage or the current or the anything in this circuit. Secondly, the ammeter, if I wanted to measure the current through that resistor, could be placed at any point in this circuit as long as the ammeter is in series. As long as the ammeter is in series with the resistor. And the reason why the ammeter needs to be in series is because two things in series have the same current. And if I'm making a measurement of the current, then I need the ammeter to be in series with the thing that I want to take the measurement of. So that ammeter needs to be in series, and it is designed to have zero resistance. And let's think about why this might be the case. If the ammeter has zero resistance, then as the current flows through the resistor, unimpeded, it will flow through the ammeter. And although the current in the resistor and the current in the ammeter has to be the same no matter what, because physically there's not another path to travel along, if that ammeter had any resistance to it, then it would affect the current in the circuit. The equivalent resistance would be different. So we want to add a device to the circuit that is capable of measuring the current, and it has to be that same current as the resistor, but without altering the total current in the circuit. And for that reason, the ammeter is designed to have zero resistance. So in summary, a voltage is designed to have infinite resistance and must be placed in parallel. An ammeter is designed to have zero resistance and must be placed in series. Now I'd like to talk a little bit about power, which is related to the rate at which energy is being dissipated by different circuit elements. So in general, if there is a light bulb that is in a circuit and that light bulb has light coming off of it, that must mean that there's some current that's flowing through that bulb. And so what's happening is current is flowing across that bulb, energy is being dissipated, and we see that energy being dissipated as light. We also know that energy is being dissipated because if we touch the light bulb, it's hot. And so clearly there's some energy losses. And that's where the battery has to be there to provide more energy, because there's constantly being energy loss due to the fact that energy is being dissipated by different circuit elements. So in general, the equation for power is current times voltage. And because of manipulations that I can make with Ohm's law, the voltage could be represented as I times R. And so we could express power as the square of current times the resistance. Or if we replace the current with V over R, then we could express the equation for power as V squared over R. And it could be shown that the power dissipated by a circuit element is directly related to the current, as I say up above. So if the current goes up, then the power dissipated by that circuit element will go up. And the reason why that's important is because if you start to be asked questions about the power dissipated by a circuit element, you need to look at the current, how much current is flowing through that object, in order to determine how much power is going to be dissipated. And the way that I also think about that qualitatively is for light bulbs. The greater the current through the light bulb, the brighter it will be, the more power being dissipated. So there's a direct relationship between power and current, and there's a direct qualitative relationship between power and the brightness of a light bulb. And lastly, I'd like to say that in terms of power, we've previously used a power equation to describe mechanical things like somebody running up a staircase or speeding up on a bicycle. And so power can also be defined as the rate of change in the energy of an object, or the rate of the dissipation of that energy. And so we could also set power equal to delta E over delta T, where E represents the energy dissipated measured in joules, and T represents the amount of time it took to dissipate that energy. And since energy is always measured in joules and time is always measured in seconds, then a joule per second is the same as the units for watts, is the same as the unit for power, and instead of writing joules per second, we use the unit watts, which hopefully makes a lot of sense because when we go to purchase a light bulb, the power rating on that light bulb is given in watts. This next part serves to remind you of the differences and the similarities between series and parallel circuits. Every single circuit that you see on an AP Physics 1 exam will either be a series circuit, a parallel circuit, or some combination of series and parallel parts of circuits. And so for that reason, whether you're staring at an entirely series circuit or a section of a circuit that is in series, these 3 bullet points are going to apply. So first, the equivalent resistance, Rs, for a series circuit is found by just adding up the resistance of all the resistors in the circuit. And so if you know what R1, R2, and R3 is, you just add those 3 numbers up together to get the equivalent resistance. And remember, the equivalent resistance, what that means, what that represents is if I wanted to make a simpler circuit where I removed R1, R2, and R3 and I replaced it with a single resistor, but I wanted the properties of the circuit to be the same, then I need a rule for describing that equivalent resistance. I need a rule for how I add up the resistors to simplify the circuit. That's what the equivalent resistance does. So Rs is the value of that single resistor that would replace the 3 that I originally drew. Because there is only one path in a series circuit, the current everywhere in that path is the same. So the current flows out of the battery, and at this point, this point, this point, this point, this point, the current is the exact same. The current in a series circuit is the same everywhere, even after it's gone across the resistor, moved across the battery. And that is a statement of the conservation of charge. If the amount of charge flowing past a point at point A is a certain amount, then that same amount of charge needs to be flowing past a point at point B, because the charge cannot be accumulated anywhere. Because if there was a buildup of charge, there would just be a bunch of charge behind it ready to push it out of the way. Okay, so the current everywhere in the series circuit is very much the same. However, the voltage among the elements in a series circuit is going to be split. And so if the total voltage of this battery is V for the series circuit, then each of the resistors is going to receive some fraction of that total voltage. Each resistor will have a voltage drop across it that is equal to some fraction of V. Now, if each of those resistors has an equal resistance, then each resistor will receive 1/3 of the total voltage. But if one of those resistors has a greater resistance, there will be a larger voltage drop across it. And so now what's different about the parallel circuit? So first of all, I noticed that in the parallel circuit, the current comes out and there are multiple places for it to go. The current could go this way or it could continue straight. It could go this way or continue straight. And so for that reason, there are multiple paths. And we need to remember that a parallel circuit is defined as having multiple paths. And so for a series circuit, the current was the same everywhere, but that's not going to be true in the parallel circuit. In the parallel circuit, the current actually splits up into each of those branches. And you might imagine that if the resistance of every single branch in that circuit was the same, then the current in every single branch in that circuit would also be the same. But more likely than not, the resistance of one or more of the branches might be different than the other branches. And if that's the case, then the current will split unevenly. Alright, so the amount of current that goes into each branch in a parallel circuit depends on how much resistance is in that branch. And one of the things that we learned is that if there are only two branches, for example, and one of those branches has twice as much resistance, then it will have half as much current. And so sometimes we can get information in a circuit fairly quickly by just thinking about the ratio of the resistance to the current. If they have the same resistance, same current. If one has 1/3 the resistance, it will have 3 times the current. And lastly, the voltage across each branch of a parallel circuit is going to be the same. And the reason for that, as I said previously, voltage at a particular point is associated with the point, and differences in voltage, or potential differences, are associated with the difference in potential between two different points on a circuit. And we have to remember that this point that I'm drawing, this point that I'm drawing, and this point I'm drawing, because there is no circuit element between those 3 points, those 3 points are equivalent in this circuit. And the same is true at the bottom. So these 3 points are equivalent, and these 3 points are equivalent in this circuit. And what I notice about those points is they're directly connected to the 2 terminals of the battery. There's nothing between those points and the battery. And so for that reason, it could be said that every resistor in this circuit is connected directly to the battery. So every resistor in the circuit not only gets the same voltage, but they get the same full voltage of the battery. And so in general, you should expect that the voltage of every single element in a parallel circuit is going to be the same. Now, what that means for us is if each circuit element is getting the full voltage of the battery, then the battery for the parallel circuit is going to die quicker than the battery for the series circuit. So let's say that I take resistors R1, R2, and R3, and I have two resistors R1, 2 resistors R2, 2 resistors R3. And I have 2 identical batteries. I hook up the series circuit, I hook up the parallel circuit. Because the parallel circuit is drawing more voltage from the battery, because each one receives the full voltage of the battery, those light bulbs will be brighter. And not only will they be brighter, but because of that extra brightness that you can observe, you know that the battery in the parallel circuit is going to die faster than the battery in the series circuit. In the series circuit, the voltage is split. Each one only gets a fraction of that total voltage. The light bulbs will be dimmer, but the battery will last longer. And so for that reason, it should make some sense that for a series circuit, the equivalent resistance always goes up. If I add more resistors to a series circuit, the equivalent resistance will go up. Because if I add another resistor, the voltage is now split among the 4 resistors, and so the current drops. Each one experiences even less voltage drop. All the light bulbs are becoming more and more dim. But if I add, and this is strange, if I add another resistor to a parallel circuit, the equivalent resistance will go down even further. And so when I find the equivalent resistance, I need to remember that I do 1 over R1 plus 1 over R2 plus 1 over R3, and then I'm going to hit equals in my calculator. And then in order to find the equivalent resistance, which is on the denominator of this fraction, which is kind of weird, I would then need to take the reciprocal of my answer. And regardless of the values of R1, R2, and R3, what you will find is that the equivalent resistance of a parallel arrangement is always less than the least or smallest resistor. So if R1, R2, and R3 have resistances 3, 4, and 5, then the smallest resistor was 3 ohms. The equivalent resistance of that arrangement will always be less than 3 ohms. So in general, the equivalent resistance of a parallel arrangement will always decrease. And if I add another resistor, that's another resistor pulling more voltage from the battery that's equally bright. The battery is going to die even sooner, but the equivalent resistance goes down because in order to provide that same voltage difference across each resistor, even when the new one is added, there has to be more current that's pulled out of the battery. And that is corresponding to a decrease in the resistance. The last two things that I want to talk about are Kirchhoff's junction rule and Kirchhoff's loop rule. The junction rule and loop rule are two rules that we can use to help us analyze a circuit. And they get applied in the following way. First, let's start with the junction rule, which makes a lot of sense. Let's say that I'm going to identify point A as being a junction and point B as being a junction. What the junction rule says is that the currents going into the junction, so here going into point A would be this current, and then coming out of that junction I would have 1, 2, 3 currents. What Kirchhoff's junction rule says is that the amount of current that's going in, maybe I'll call that I1, is equal to the amount of current coming out, and maybe I'll call these I2, I3, and I4. And so the junction rule at point A could be applied to say that I1 equals I2 plus I3 plus I4. And the analogy that I've often given is that if there are 100 cars that approach a four-way stop sign, there are 100 cars that need to leave the four-way stop sign. The number of cars that come into the junction and leave the junction is the same. And electrons do the same thing. The number of electrons that arrive at point A need to leave point A, and so the currents coming in and the currents coming out are the same. And at point B, we would do the same thing to say that the currents coming in, which is currents 2, 3, and 4, needs to be equal to the currents coming out. So I2 plus I3 plus I4 needs to be equal to the current coming out. And while I wasn't really planning on talking about it in this way, one important thing that we get here is I already wrote an equation that says I2 plus I3 plus I4 is equal to I1. And now I have an equation that says I2 plus I3 plus I4 is equal to, and it must also still be, I1. And that's one reason, or one thing that helps us remember that the current everywhere in a series circuit is the same. What I mean by that is, yes, these three resistors that I have drawn are in a parallel arrangement, but that parallel arrangement is in series with these other two resistors. So what I mean by that is I could combine the three parallel resistors into a single resistor, and then I could say that these three pieces of the circuit are in series. And so if the current through this red box on the left is I1, then the current through this box on the right must also be I1. Therefore, all of the currents within that box number 2 in those three resistors needs to add up to I1. So that's how the junction rule might be applied. The loop rule is something that's a little bit more tricky to understand, but is equally important. What the loop rule says is that if I start at a particular location in a circuit and I go in a loop around any loop that I want around the circuit back to that same point, that the sum of the voltage rises and voltage drops across all the circuit elements that I go around in my loop, and I can pick the loop in any way that I want, is equal to 0. And so what does that look like physically? So if we started at this point and we travel across the battery, there's going to be a voltage rise equal to the voltage of the battery. So maybe I'll call voltage rises positive. As I flow across a resistor, there is going to be a voltage drop. And typically in a circuit, you're not just told what the voltage drop is, you might be told what the resistance is. And you could simplify this circuit in order to figure out what the current through that resistor is. And then you would know the current and the resistance, so you could calculate the voltage. And by Ohm's law, the amount of voltage drop across that resistor would be equal to the current through it times the resistance of it. So there is a voltage rise, positive, across the battery, and then a voltage drop, negative, across the resistor. The next thing that I'd like to point out is, let's say that one of these resistors right here has a voltage of 1 volt. How could we proceed? Do I have to add 3 more terms to this equation for each of those resistors, or is there a more clever way of thinking about this? Well, first off, I know that if the voltage drop across this resistor is 1 volt, then the voltage across those 2 resistors is 1 volt, and the voltage across this resistor is also 1 volt, which means the potential difference between these 2 equivalent points in the circuit is 1 volt. Therefore, I could draw a more simplified circuit that looks like this, where these 2 points across this equivalent resistor have a potential difference across them of 1 volt. And so what that means is, if I encounter a set of a couple of resistors in my loop rule equation, as I'm writing Kirchhoff's loop rule, I don't need to find the voltage of each one of those things and add them up. What I need to do is just find the voltage across one of them, and that represents the voltage across the 2 terminals of those 2 points. So maybe I know what that voltage is, and so there's a voltage drop, which maybe I'll call like V1. So sometimes if you know the voltage, you could just plug it in, minus V plus V. And if you don't know the voltage, then you need to know the current and the resistance, and the voltage drop might be expressed as I times R. And I keep going around this circuit. I go through the parallel arrangement, that's where I get the minus V1. And then I flow through this last resistor, which maybe again, I don't know what the voltage is, but I do know that it has the same current, I, but maybe a different resistance. So maybe I'll call those resistors, RA and RB. But importantly, resistors RA and RB have the same current because those 2 resistors are in series with one another. If they had different currents, I would need to specify that in my loop rule equation. Now that I've arrived back at that same point, I know that this equation is equal to 0. And the reason why this is useful is because if I have this equation, let's say the voltage of the battery was known, and let's say the 1 volt across that parallel arrangement was known. If I was also told what the value of the resistor RA was and the value of the resistor RB was, I could very easily calculate the current that flows through this circuit. I would add some of those terms to the other side and solve for the current in that circuit. And so therefore, the sum of the voltage rises and drops as you go around a closed loop in a circuit could be a powerful tool for measuring some things in a circuit. So that's about it. The last thing that I want to leave you with in terms of circuit problem solving is to please remember that most circuit problems, there's some intuitive things like, oh, because it's in series, the currents are the same. Because it's in parallel, the voltages are the same. And so there are some intuitive things that maybe you can pick up on right away. But in principle, if you are solving a long circuit problem, what happens is this. I take the complicated circuit, I combine things that are in series and in parallel to find their equivalent resistance. I simplify the circuit as much as possible. Once it's simplified, I can probably find the total current in that circuit. Now that I know the total current, that's an added piece of information, I can build the circuit back up and look at the more complicated versions of my circuit diagrams to find new resistances, new voltages, things like that. So make sure that you have a plan for how you're going to attack circuits. We have Ohm's law available, we have the junction rule, the loop rule, and our knowledge of what's true about series and parallel circuits.